Separable 4 points fundamental matrix. One of the basic building blocks in computer vision is the computation of epipolar geometry, given a set of putative image point correspondences. Often, such correspondences include mismatches, therefore a robust estimation method needs to be carried out. The most common method used is RANSAC. One of its key limitations is that in the presence of a considerable amount of mismatched points correspondences, a large number of hypotheses evaluations is needed in order to obtain a reliable model. We present a method that can markedly reduce the number of RANSAC hypotheses evaluations beyond the current known minimum. For example, on the left side, we can see that our approach requires only 896 RANSAC iterations, while using standard RANSAC with the 7 points algorithm requires 7,025 iterations. 7.8 times more iterations. Our method can reduce the minimal number of RANSAC hypotheses evaluations beyond the current known minimum. Using the 7 points algorithms, our approach requires less iterations than existing methods. Our approach, similar to approaches that require less than 7 correspondences, assumes additional knowledge. We require that a single line segment exists in the image with 4 correspondences and show experimentally that such a configuration is common. Given such a configuration, we show that our approach guarantees a minimal number of hypotheses evaluations. In cases where such a configuration does not exist, standard RANSAC can be applied with overall small overhead. We compute the fundamental matrix in 2 steps. In the first step, we sample 3 points on a line segment. We compute the epipolar homography and validate its goodness of fit using at least one additional point, without the full computation of the fundamental matrix. In the second step, the recovered matches are fixed and the remaining points matches are recovered by sampling, without any restriction. Our approach for RANSAC-based computation of the fundamental matrix is based on epipolar homography decomposition. Existing methods for the computation of the epipolar homography require the knowledge of at least 3 corresponding epipolar lines and, as a consequence, are rarely used in practice. We show how to compute the epipolar homography without a priori knowledge of epipolar lines. We efficiently find 4 correspondences on lines across images. For each image, our approach does not require knowledge of the points and lines in the other image, which allows parallel implementation. The key idea is to use Huff transform to detect the lines independently in each image and update a joint accumulator, which can be queried only after the process is completed. See paper for more details. We conduct experiments on real-world datasets and showed that 4 correspondences or more on image lines are common. Here is an example for such correspondences recovered by our approach. The red points are the matched putative point correspondences which are aligned on line segments, colored in blue, in the image planes. And another one. And another one. Based on the matched points and line segments, we use our reformulation to compute the epipolar homography and reduce the required number of RANSAC iterations for the full computation. The red points are the matched putative point correspondences which are aligned on line segments in the image planes. The green lines are epipolar lines which are not known a priori and do not take part in the matching process. We show experimentally that our approach practically reduces the required number of iterations with respect to different approaches. Check out our website for the paper and code. Thank you for watching us.